What if everything we thought we knew about black holes was incomplete? For decades, physicists believed they had reached the end of the story. A black hole forms, it evolves, it settles down, and then nothing. No surprises, no hidden activity, just a quiet cosmic object slowly fading away. But that picture turns out to be wrong. Because even when a black hole looks perfectly calm on the outside, something extraordinary is still happening deep inside. Something no one expected. Black holes don't just sit there, they compute. And they never stop. For a long time, the standard view of black holes was straightforward. A massive star collapses, or matter compresses beyond a critical point, and a black hole forms. In the beginning, it's chaotic. Matter rushes inward, the event horizon expands, and entropy, the measure of disorder, rises rapidly. This is the black hole's early stage, a period of intense growth and change. Everything about it is dynamic, unstable, evolving, but eventually, that chaos fades. The black hole settles into what physicists call thermodynamic equilibrium. Its temperature stabilizes at a fixed value, extremely low but constant. Hawking radiation begins to flow out at a steady rate. And most importantly, the entropy stops increasing. It reaches a maximum and levels off. At that point, the assumption was simple. The system is done evolving. This idea comes straight from everyday experience. Think about a hot cup of coffee sitting on a table. At first, it cools quickly. Heat flows into the room and the temperature changes. But after some time, it matches the temperature of its surroundings. At that point, nothing interesting happens anymore. The system has reached equilibrium. That's the end of the story. Physicists believe black holes behave the same way. Once entropy reached its maximum, once all the information inside was fully scrambled, there was nowhere left to go. The system had exhausted its possibilities. Sure, time would continue, and the black hole would slowly evaporate through Hawking radiation, but its internal quantum state, that was considered finished, static, and unchanging. This perspective was built on groundbreaking discoveries from the 1970s. Stephen Hawking showed that black holes emit radiation and therefore have a temperature. Before that, Jacob Bekenstein had proposed that black holes also have entropy, and remarkably, that entropy is proportional to the surface area of the event horizon, not the volume inside. Specifically, 1/4 of the horizon area in Planck units. That idea changed everything. It meant black holes weren't just gravitational objects, they were thermodynamic systems. They followed the same kinds of laws as heat and energy. But it also reinforced a powerful assumption. Once a black hole reaches maximum entropy, its evolution is effectively over. And for years, that assumption felt completely natural. Even I accepted it without hesitation. The entropy plateaus, the system stabilizes, and that's it. From a thermodynamic point of view, nothing meaningful continues to happen inside the black hole. But there was a flaw in this picture, and it was hiding in plain sight. The problem only becomes obvious when you stop looking at the black hole from the outside and instead imagine falling into it. From that perspective, time doesn't stop. Nothing freezes. If you cross the event horizon, assuming nothing destroys you instantly, you continue to experience time normally, you fall inward, the geometry around you continues to evolve, events unfold, things happen. So here's the contradiction. From the outside, the black hole looks static. Its entropy has stopped growing. But from the inside, time is still moving forward, and the system is still changing. How can both of these be true at the same time? Entropy is supposed to measure how much information is scrambled. If it's already at its maximum, then what exactly is still evolving? What is the black hole doing with all that time? This question lingered, quietly unresolved, until around 2014. At the time, the physics community was deeply engaged in another controversy known as the black hole firewall paradox. This was a serious challenge to our understanding of black holes, suggesting that older black holes might have a violent barrier at the event horizon. I had been working on a different idea, known as ER equals EPR, which proposed that quantum entanglement is connected to wormholes in spacetime. That helped address some of the issues raised by the firewall paradox, but it didn't solve everything. One question remained stubbornly open. What is actually happening inside an old black hole? It was during this time that a new way of thinking began to take shape, one that didn't rely on entropy alone. Because maybe, just maybe, entropy wasn't the full story, and that realization would change everything. In the next part, we'll uncover the missing concept that rewrites black hole physics entirely and reveals what these objects are really doing behind the scenes. The idea that entropy might not tell the whole story didn't arrive as a dramatic breakthrough. It started as a quiet discomfort, a feeling that something important was being overlooked. If black holes truly stopped evolving once they reached equilibrium, then why did their interiors still seem active? Why did time keep flowing for anything inside them? That tension refused to go away. Around that time, I was working closely with Adam Brown, a sharp and deeply intuitive thinker. One afternoon in my office, during a conversation that didn't seem unusual at first, he said something that completely shifted the direction of our thinking. He asked, "What if entropy isn't the whole story? What if there's another quantity that keeps growing even after entropy stops?" That single question opened the door. To understand why, you have to step outside traditional thermodynamics and look at a field that was rapidly gaining momentum during the 2010s, quantum information theory. In that world, researchers study not just how information exists, but how it changes, how it spreads, and how difficult it is to manipulate. And that's where a new concept enters the picture: computational complexity. At first glance, complexity sounds similar to entropy, but they measure very different things. Entropy tells you how scrambled a system is. Complexity tells you how hard it would be to undo that scrambling. In other words, entropy is about randomness, while complexity is about effort. Here's a simple way to picture it. Imagine you have a perfectly ordered deck of cards. You shuffle it once, and the order becomes slightly mixed. Shuffle it again, and the randomness increases. After enough shuffles, the deck reaches a point where it's effectively random. At that stage, the entropy has reached its maximum. You can't make it more random than it already is. But now, keep shuffling. The deck doesn't become more random, but something else changes. It becomes increasingly difficult to reconstruct the original order. The number of steps required to undo the shuffling grows larger and larger. That's complexity. It continues to increase even after entropy has stopped. This distinction turned out to be crucial. So we asked a simple but powerful question. Could the same thing be happening inside a black hole? Even after entropy reaches its maximum, could the complexity of its quantum state continue to grow? If the answer was yes, it would completely change how we think about black holes. It would mean they don't stop evolving at equilibrium. Instead, they continue processing information in a deeper, more subtle way. This idea wasn't immediately obvious, and to be honest, it took time to fully appreciate its implications. For months, it lingered as a possibility rather than a conclusion. But the more we explored it, the more it made sense. Quantum systems don't just maximize entropy, they also evolve in terms of complexity, and that evolution can continue for incredibly long periods of time. In fact, complexity can keep increasing for times that are exponentially large compared to the size of the system. That's not just a little longer, it's unimaginably longer. If black holes followed this rule, then they weren't static objects at all. They were active systems, continuously evolving, even long after reaching thermodynamic equilibrium. At that point, the idea became too important to ignore. In 2015, Adam and I began working on it seriously. Soon, we were joined by Daniel Roberts and Brian Swingle, both experts in quantum information and holography. Together, the four of us started digging into the problem from every angle we could think of. We spent long hours at whiteboards, filling them with equations, diagrams, and half-formed ideas. The central challenge was clear. How do you define complexity in a way that connects quantum information theory with general relativity? These are two very different frameworks, and bridging them is never straightforward. But we had one powerful tool at our disposal: ADS, CFT correspondence. This duality, originally proposed by Juan Maldacena, tells us that a theory of gravity in a higher dimensional space can be equivalent to a quantum field theory on its boundary. In simple terms, it allows us to translate problems in gravity into problems in quantum mechanics and vice versa. Within this framework, there's a fascinating structure known as the Einstein-Rosen bridge, a kind of wormhole that connects two regions of space-time. This structure isn't static. It grows over time, even when the black hole itself is in equilibrium. That growth had already been linked to entanglement in earlier work, including my own. But now we started to wonder, what if this growth isn't tracking entropy at all? What if it's tracking complexity instead? That question led us to a deeper exploration of space-time geometry. And eventually, it brought us to a concept that would become central to everything that followed. A specific region inside the black hole, defined by the paths of light rays extending from the boundary. A region that keeps expanding, even when everything else appears to have stopped. This region is called the Wheeler-DeWitt patch. And what we discovered about it would change the story completely. Because hidden inside that growing region was a quantity that never stops increasing, even when entropy does. In the next part, we'll dive into this discovery and the bold idea that connects the geometry of space-time to the growth of complexity itself. When we turned our attention to the Wheeler-DeWitt patch, everything began to click into place. This region, defined by the paths of light rays that spread out from the boundary, is more than just a curious feature of black hole geometry. It holds the key to understanding what happens after a black hole reaches equilibrium. In essence, the Wheeler-DeWitt patch is a specific region inside a black hole that describes the geometry of space-time in its interior. It's named after two physicists, John Wheeler and Bryce DeWitt, who developed it in the 1960s as part of their work in quantum cosmology. The idea behind the patch is that it captures the structure of space-time in a way that's deeply connected to the dynamics of the black hole. Here's the key point. The volume of this patch, or more precisely, the action calculated over it using Einstein's equations, keeps increasing over time, even after the black hole has reached thermodynamic equilibrium. Even after the entropy plateaus, the action continues to grow. And the most surprising part? This growth happens linearly with time, but it doesn't stop. It persists for an exponentially long period. This was a game changer. Adam and I were working alongside Dan and Brian, trying to make sense of these findings, and it became clear that we were on the verge of something monumental. The growing volume of the Wheeler-DeWitt patch is linked to the complexity of the quantum state on the boundary. In other words, the geometry inside the black hole is directly related to the computational complexity of the quantum state that describes it. We took a step back to fully understand what this meant. The quantum state on the boundary, the one that we can describe using quantum field theory, isn't just sitting there doing nothing. It's becoming exponentially harder to describe, to simulate, to understand. And the more we delved into this, the more we realized that the black hole wasn't just sitting still. It was, in a sense, actively computing, constantly working to evolve its quantum state in a way that made it increasingly complex. But that still left one crucial question. How do you measure this complexity? It's not as straightforward as entropy, which is a well-defined quantity. Complexity, by contrast, is more subtle. It's about how hard it is to undo the scrambling of information in the quantum state. And this is where the beauty of the Wheeler-DeWitt patch came in. By using the action calculated over this region, we found that the complexity of the quantum state on the boundary and the growth of the action in the bulk were equivalent. This wasn't just a coincidence. It was a profound connection between the geometry of space-time and the evolution of quantum states. We had a new way of thinking about complexity, one that tied it directly to the fabric of space-time itself. We had a bold conjecture now. The computational complexity of the quantum state on the boundary equals the classical action of the Wheeler-DeWitt patch in the bulk. In simpler terms, the growth of complexity in the quantum field theory on the boundary mirrors the growth of the space-time region inside the black hole. This was an astonishing revelation, one that opened up a new way of thinking about black holes and their behavior over time. To be clear, this wasn't something we could prove rigorously right away. This was still a conjecture, a hypothesis that needed further validation. But the beauty of it was that it solved the puzzle we had been grappling with. It explained what was happening inside black holes after they reached equilibrium. The black hole doesn't just stop, it continues to evolve, and it does so by increasing its computational complexity. We published this idea, what we now called complexity equals action, in 2016. The paper was published in Physical Review Letters, one of the most prestigious journals in theoretical physics. The reaction was immediate, and it sparked a wave of interest in the community. Some physicists were enthusiastic about the new way of thinking it presented. Others, however, were skeptical. After all, this was a conjecture, not a proven fact. It wasn't something you could derive from first principles. But the more we examined the idea, the more we were convinced that we were on the right track. The key to understanding the significance of this conjecture lies in its implications for the way black holes process information. The idea that black holes are computing, that they continue to evolve and grow in complexity, has deep consequences for how we think about the information paradox. For decades, we've wrestled with the question of whether information can escape a black hole or whether it is lost forever. Hawking's original theory suggested that information inside a black hole is lost, destroyed by the singularity at its core. I argued that the information doesn't disappear. Instead, it escapes in the form of Hawking radiation, though it's encoded in such a complex way that decoding it requires an exponentially large number of operations. This was the insight we were working toward. Complexity equals action explains why the information is so hard to decode. It's not just scrambled, it's locked behind a computational barrier. The black hole is actively scrambling and processing the information, making it increasingly difficult to extract. This isn't just theoretical, it's something that can, in principle, be measured, though we don't have the tools to do so yet. But that's not all. Complexity equals action also has profound implications for other aspects of black hole physics. Take the firewall debate, for example. Some physicists argued that old black holes should have a violent firewall at the horizon, a kind of last-ditch defense against anything falling into the black hole. I disagreed, arguing that quantum entanglement and complementarity were the real answers. But complexity provided another perspective. The barrier to building a firewall isn't just theoretical, it's computationally intractable. In other words, it's exponentially difficult to create a firewall, even if you tried. The computational complexity involved in doing so is simply too high. However, in some hypothetical situations, such as if the radiation were somehow trapped inside a black hole, this computational barrier could break down over extremely long timescales. But that's an incredibly unlikely scenario. In most cases, the complexity barrier remains insurmountable, which is why we don't see firewalls in real black holes. In the next part, we'll explore even further how complexity is reshaping our understanding of black holes, and how it's playing a central role in other areas of physics. The journey we're on is just beginning, and the implications are only getting more profound. As we dove deeper into the implications of complexity equals action, it became clear that the discovery wasn't just changing how we think about black holes, it was reshaping the very foundations of quantum gravity. The connection between complexity and the growth of spacetime inside a black hole doesn't just tell us about the interior of these enigmatic objects. It also opens a new lens for looking at the universe itself, at the way quantum systems evolve, and at the fundamental structure of reality. One of the most exciting aspects of this work was that complexity wasn't limited to black holes alone. The concept of computational complexity, which had its roots in quantum information theory, was suddenly showing up everywhere in quantum gravity. From quantum chaos to quantum error correction, from holography to the study of gravitational dynamics, complexity was proving to be a central idea. It was no longer just a curiosity, it was a fundamental ingredient in understanding how the universe works at the deepest level. Take quantum chaos, for instance. This area of study looks at how quantum systems behave in the presence of small perturbations. Classical chaos deals with systems that are highly sensitive to initial conditions. Small changes can lead to radically different outcomes. In quantum mechanics, this sensitivity is encoded in the complexity of the system. The more complex the system, the harder it is to predict its future behavior, and the more challenging it is to reverse the processes that led to its current state. By applying complexity to quantum chaos, we started to see connections between seemingly unrelated fields. Complexity was showing up in places we hadn't expected, and each time it did, it brought new insights. It was becoming clear that complexity was not just a theoretical tool. It was something real, something that could help us understand how quantum systems evolve and how space-time itself behaves under extreme conditions. Then there was the connection to holography. Holography, particularly the ADS CFT correspondence, has already revolutionized how we think about gravity and quantum field theory. This duality tells us that gravity in a higher dimensional space can be equivalent to a quantum field theory in a lower dimensional space. And now, with complexity entering the picture, we saw even deeper connections between geometry, quantum states, and the evolution of information. It wasn't just that black holes were connected to quantum information, they were quantum computers themselves, processing information in ways that had previously been unimaginable. In fact, this idea was no longer just speculative. It was beginning to have practical implications. In 2020, my collaborators and I, Adam, Jaber Saras, Jeff Pennington, and I published a groundbreaking paper showing that geometric obstructions in space-time make it impossible to decode Hawking radiation until very late times. This paper introduced the concept of the Python's lunch, a geometric barrier that grows as a black hole evolves. The complexity of the system is hidden behind this barrier, making it nearly impossible to decode the Hawking radiation until a significant amount of time has passed. What's truly fascinating about the Python's lunch is that it provides a mathematical description of the complexity barrier in a way that was previously unimaginable. The concept is simple. There's a region of space-time where information is locked behind a growing barrier. The complexity of the quantum state makes it exponentially hard to extract the information from the black hole. This barrier could explain why Hawking radiation is so difficult to decode. It's not just scrambled, it's actively being kept behind an exponentially growing computational wall. This breakthrough was another step toward understanding the fundamental role that complexity plays in black hole physics. It was another piece of the puzzle that had been missing for so long. And it reinforced our conjecture that black holes are not static, dead objects. They are active, evolving systems that process information in ways that are both subtle and profound. But this work didn't just impact black hole physics, it also had broader implications for the entire field of quantum gravity. The connection between complexity and spacetime was beginning to suggest that complexity might be a universal feature of quantum systems. It could be the key to understanding the evolution of spacetime itself, from the earliest moments of the universe all the way to the deepest regions of black holes. I began to realize that complexity was going to be just as fundamental to quantum gravity as entropy had been to thermodynamics in the 1800s. Just as entropy revolutionized our understanding of thermodynamics, complexity was poised to do the same for quantum gravity. It was the next layer of understanding, something deeper, something more subtle, and yet something incredibly powerful. But there was still much work to be done. We didn't have all the answers yet. Complexity was still a relatively new concept in the context of gravity, and we had barely scratched the surface of its potential applications. We didn't even have a complete definition of complexity in a fully general background independent way. We were still in the early stages of figuring out how to apply it to different systems. Even so, I was convinced that we were on the right track. The work we had done, the papers we had published, the connections we had uncovered, these were just the beginning. Complexity was going to be a central theme in the next phase of theoretical physics. And the best part? This wasn't just abstract theory anymore. In 2022, Google's quantum computer successfully simulated wormhole dynamics using ideas directly drawn from the work on complexity. This was a huge step forward. The idea that quantum computers could simulate gravitational systems, something that was once purely theoretical, was now becoming reality. The work on complexity was moving from the realm of ideas to the realm of testable physics. In the next part, we'll explore how complexity continues to reshape our understanding of the universe and how it's becoming a driving force in some of the most exciting areas of modern physics. The journey is far from over, and the surprises are only beginning.